to be on the associative memories. But of course, before we initiate this topic, I mean, whatever we were discussing in the last class, that's to say, we were discussing about the learning mechanism, and in that we were especially discussing, I mean, towards the end of the last class, we were discussing about the competitive learning, okay, where we have to see one or two more aspects of it so that the concepts go very clearly in our minds. And then we are also going to consider the last aspect of learning, which is the Boltzmann, because as you remember that we had listed 5 categories of learning. So we have done 4 of them, and the 5th one, that is Boltzmann learning, is still the one that we have to do. And after we finish of that, we will begin with the topic for the today, which is associative memory. So I don't know that how much of it I can cover today, but at least today I will at least make an introduction to the associative memory, and to the extent possible I will go into the depth of it. Okay. So this is going to be the topic of today, and let us continue the discussions that we were having in particular about the competitive learning. Now, there are a few questions which I think can come to the mind of all of you, and that is to say that, well and fine, we have a network, okay, let's say, I mean, certain number of inputs are there, and we have got some outputs. In fact, the number of outputs that we are going to have for the competitive network is, competitive learning network is going to be equal to the number of classes that we would like to have. In fact, what type of network is it? Is it supervised or an unsupervised type of learning? What kind of category would you put it into? Supervised, unsupervised? Unsupervised, clearly unsupervised. Why? Because here we are not providing any desired response to it. Okay, we are allowing the network to evolve on its own. So what happens is that, I mean, we will be having certain number of input units, we will be having some number of output units, and the interconnection would be made like this. Okay, so that this input to output will be having their own synaptic weights, all right, and then the competitive learning networks, as we said, that goes through a process of winner takes all, in the sense that one of the output units, okay, will win the competition, and that will actually classify the pattern. Okay, that is to say, for a given input pattern, one of these outputs would be the winner. So it could be that if you feed a different pattern next time, okay, then another network could become the winner. So it all depends that how the interconnection weights between them are adjusted. Okay, and the learning mechanism that we had seen in the last class, okay, clearly said that the delta WKJ, that's going to be equal to eta times xj minus wkj, so that you had seen that there is a very clear preference for the or rather to say, we should put it this way, that the weights that we are going to have is ultimately going to be aligned to the input pattern, because I mean, for a given output neuron K, okay, if it is having connections to many different inputs, okay, then the synaptic weights which will be given by WKJ, that has to get aligned to XJ. Now, if it gets aligned to that, that means to say what? That means to say that next time you repeat the same pattern, all right, now the weights are already aligned for that, okay, and there is a greater chance that, or rather, I mean, it's not a matter of chance, it is inevitably going to happen, that if it is a winner in the earlier step, okay, then for I mean, when the pattern is going to be presented for the next time, okay, the same output unit is definitely going to be the winner. In fact, it will be winner in a stronger sense. Why? Because the weights have been already aligned. Okay. Now, let us try to get this concept in a in the form of some kind of a geometrical interpretation. Let us say that we have got 3 input neurons. Okay. Supposing we have got input neurons which we are calling as, let us say, their inputs are x1, x2 and x3, and let us consider, okay, 2 outputs. Let us say that we have the output units to be y1 and y2, they are the respective outputs. So, we are going to call all these weights as W11, okay. This one will be W12 and this one will be W13, and likewise for 2 we are going to have it as W21, 22 and 23. Anyway, so here let us also put some constraint that the in this case this x, that is going to be in the form of a vector. So, if we define x as a vector, then its elements will be x1, x2 and x3, and supposing we define that the magnitude of this vector is equal to unity. Okay. That means to say what? If we define that this is equal to unity, this means to say that x1 square plus x2 square plus x3 square, that is going to be equal to 1. But we can have large combination of patterns realized out of it. Given the 3 inputs x1, x2 and x3, we can realize a large number of patterns. Now, what will be, where will these patterns lie? Okay. What will be the locus of all these patterns? In which space are they going to lie? Sphere. It is going to lie on the surface of a sphere. So, in this case, we have got 3 inputs x1, x2 and x3. Okay. Had there been just 2 x1 and x2, it would have been a circle, the locus would have been a circle, but because we have got x1, x2 and x3, the locus is definitely going to be a sphere. So, we can imagine that there is a sphere, okay. The sphere is going to have a center from which the vector will be originating, and we will be having, for different patterns, we will be having the vectors positioned in different spaces. Okay. Let us say that now we are going to designate the vectors by x1 vector, x2 vector, x3 vector, like that. So, I am going to consider x1 vector, x2 vector. Mind you, these are different from x1, x2, x3, because this x1, x2, x3, let me write it down in lower case so as to avoid confusion. These x1, x2, x3s are nothing but scalar quantities which composes the elements of this vector. Okay. But in this case, we are going to consider the vectors x1, x2, x3, which will basically indicate the different patterns that we are feeding to a system. And how many such patterns can we feed? There is really speaking no restriction, okay, or there is ultimately going to be some restriction, that is according to the learning capacity of the network, which we are going to study later on. Okay. Right now we do not bother, right now we assume that there could be many different types of patterns that you can feed to the system. So, when you imagine a sphere, okay, maybe that the x1 vector, okay, will have its edge located over here, that means to say from origin to this point on the surface. So, it is actually being drawn as a 3D surface. Okay. This is a sphere, okay, which is a 3-dimensional surface. So, supposing that this is where we have the x1 vector, this is where we have the x2 vector, this is where we have the x3 vector, like that. Okay. Now, we are not going to have just 3 patterns, maybe 4, 5, 6, 7, large number of patterns could be there. So, maybe that here we have got another vector, here we have got another vector, here we have got another vector, like that many vectors are there. And let us say that here also near around x2 we are having different patterns, near to x3 we are having different patterns, and let us not say that we have only 2 output neurons, say that we have got neurons 1, 2 and 3. So, that means to say that this type of a competitive network competitive learning network can really classify the patterns into 3 different classes. Now, from this given example, we can clearly see that there are 3 distinct clusters of patterns which are existing, isn't it? We have got one cluster which is around this, where x1 is lying. We have got another cluster which contains x2 and also the patterns which are nearing x2. We have got another cluster of patterns which is close to x3. Okay, 3 distinct patterns are there. So, the behavior that you should logically expect out of this neural network is that one of the neurons out of these 3 outputs, okay, one of the neurons will be classifying this cluster. That means to say that no matter whether the vector is this one or this one or this one or this one, it will classify according to 1. No matter then another neuron, another output neuron will be classifying this cluster, and likewise the third neuron will classify this cluster. That is what it is going to do. Now, what exactly do we mean by alignment? So, just like the way we have assumed that the magnitude of this vector is going to be equal to unity, very similarly we can assume that the sum of the weights, okay, that is connected to every output neuron, okay, that is also going to be equal to unity. Sum of the weights means that squared value of the sum. Okay. So, what I mean to say is summation w k I, okay, and this is summed up over I, and summation w k I square in fact we should take. So, supposing we have got n inputs, so that the summation w k I square, okay, summed up over I is equal to n, that is going to be unity. This means to say what? That supposing that for this pattern x1 or the cluster that we have shown, supposing we have fed the pattern x1 vector directly. Okay. So, x1 is a vector and we fed that pattern, and supposing that for this y1 is the winner, all right. So, y1 is the winner means definitely w11, w12 and w13, these are the weights, okay, these are the synaptic weights which come into play. So, what will happen is that we are going to have w11 square plus 12 square plus 13 square equal to unity, and because the output y1 has now become the winner, this means to say what? It will go by the learning rule, it will definitely go by this learning rule, and as a result what happens? That the winner's weights will be adjusted, all the losers' weight remain the same, okay, but the winner's weight, that is to say these ones, will get adjusted, meaning that this w11, w12 and w13 will now be aligned to the x1 vector pattern. Is it very clear? That means to say that if earlier we had, I mean let us imagine in the 3D way, that if earlier this was the w vector, and what is w vector? W vector is nothing but we are defining it to be the vector consisting of, let us say, w11, w12, w13. Let us call it as w1 vector, because that is the vector that is associated with the output neuron 1. So, w1 vector was earlier like this. Supposing this is the position, or let me draw it with a different pen, that will be better. So, supposing the one which I have marked now, right now, that is the position of the initial w1, or initially w1 may be somewhere here. But then what are we going to do? We have to steer this vector, okay, towards the pattern, okay, that has caused the output neuron to be the winner. You understand? We have to, I mean, this vector is somewhere here. Supposing this is the vector that we have got over here, okay, and supposing the winning pattern is this and the vector lies here. What we have to do is to steer this vector and align it towards the winning pattern. Is this understood? Anybody having any doubt on that? So, that is exactly what we are going to do. So, that means to say what? That initially if we have the vector, okay, aligned from the center to this point, now with the adjustment of the weight, the vector will move closer to this. Okay. In fact, if for all these patterns this neuron is going to be the winner, then where would you expect the ultimate vector to get aligned, ultimately the weight vector to get aligned? To the center of the cluster. Okay. No matter in whatever manner we take the center, okay, I mean could be the centroid or whatever, I mean somewhere in the center of the cluster, okay, of the vectors for which it is the winner, there the weight should ultimately get aligned to. Okay. This is what is going to happen. So, initially you start with random weights, okay, the units 1, 2 and 3, the output units 1, 2 and 3, they will be having all random weights and you will keep on feeding patterns. And now what will happen is that with one pattern becoming a winner for one of the output neurons, okay, that output neuron's synaptic weights will now get aligned to the winning pattern. Okay. So, like this ultimately there will be 3 distinct classifications. Okay. If you have more than 3 clusters, okay, then of course there is a problem, and I think you can guess that problem. What is that problem? Because we have got only 3 output units. So, if we get more than 3 clusters, then the output units will not be very sufficient to make the cluster. So, we will be having some error. So, what happens is that if there are 4 clusters, then the 4th cluster elements can get aligned to any of the other clusters, and I mean the results will not be very good. So, in fact, that is the way whereby we have to decide about the number of output neurons when we have got a very clear cut idea about how many classes that we are going to make. So, this is more or less the geometrical interpretation of the competitive learning network. So, it is indeed going through a process of competition, and the ultimate aim is that the weight vector will be aligned to the winning pattern vector. That is the clear thing that we are going to do out of the competitive learning network. All right. Yes, any question?
What if the 2 clusters have an intersection?
The 2 clusters having intersection, well, there is a possibility that the 2 clusters are having some kind of an intersection. So, in that case what happens is that near the intersection region, okay, it can be, I mean one of them will be the winner. So, I mean meaning to say that the question that has been asked is that supposing this is one cluster, cluster 1 let us say, and supposing we have got another cluster which is cluster 2, okay, and he has said that the cluster 1 and cluster 2 will be having some kind of an intersection. So, what happens is that this is more or less the kind of an intersection zone. So, what happens is that out of this again, okay, I mean ultimately one of these will be belonging to this cluster, some neurons, some patterns will be belonging to the other cluster. So, that will again depend upon the subtle adjustments of the weights, but ultimately the 2 clusters are going to merge. So, there could be some little bit discrepancy in the results. Okay. The results are very much ideal, the classification is very much ideal when the clusters are distinct, and the number of distinct clusters that we have is equal to the number of output neurons that we have in the system. As long as that is there, the classification is very accurate. Otherwise, the classification is not that accurate. I mean, there could be some sources of error in that. Any other questions that you may be having in your mind?
Sigma WKJ
Sigma WKJ, yes,
is equal to 1.
yes. So, that was one of the, see, I mean, yeah, I mean this question is coming that last class I said sigma WKJ is equal to 1, and this class I am saying sigma WKJ square is equal to 1. This square thing I have only said from a geometrical interpretation point of view, so that we can imagine that this is on a sphere. Okay. That is the only reason why I took this to be WKI square is equal to 1. Now, this is one of the so ultimately the weights are going to have some constraint, whether you define it in the terms of summation equal to 1 or summation square equal to 1. the weights are in fact having some kind of constraints between them. It is not that you can keep on increasing the weights indefinitely. There is a limit. You have to keep a check on that. And another thing, yes, I mean I should have told you that in this case I have taken example of a 3 dimension. Okay. So, does it mean to say that I cannot take more than 3 dimension? We can definitely take. We can take 4 dimension as input, we can take 4 inputs, we can take 5 inputs, in which case our input pattern is going to be a 5 dimensional vector or multi-dimensional vector, it is going to be n dimensional vector, it is going to be. So, in that case what will be the geometrical interpretation of that? Where will the patterns lie? On the surface of unit hypersphere. Okay. So, this will lie on the surface of unit hypersphere, okay, if we imagine that summation of xi square, okay, is equal to 1, okay, that means to say that the magnitude of the input vector is equal to unity, okay, and also this is hypersphere because it is more than 3 dimensions. So, we cannot really conceptualize, we cannot really visualize the existence of this sphere, but it is definitely a hypersphere. All right. So, now let us go over to the next topic that we were going to cover on the learning aspect, and that is called as the Boltzmann learning. Boltzmann learning, okay, and we are going to cover this shortly. So, now Boltzmann learning is actually a stochastic learning algorithm. Okay. So, we have already seen about the stochastic learning aspect, the one which is not deterministic, simply that. Okay. So, this is a stochastic learning algorithm, and this is in fact derived from statistical mechanics. Okay. Mind you, at this stage I am not going over to any discussion on the statistical mechanics aspects or the details of Boltzmann learning, that we will not be doing here. We will only see in a very nutshell, okay, about the learning mechanism in it. Okay. Without going into much of details, we will cover the details if we have time towards the end of this course. All right. Now, the neurons, okay, basically constitute a recurrent structure. Okay. And the neurons in a Boltzmann learning, they constitute a recurrent structure. And what is meant by recurrent structure? That means to say that there is a feedback. I mean, there are feedbacks that exist between neurons. They are all interconnected and they are having feedback. So, neurons constitute a recurrent structure and they operate in the binary mode. So, they operate in binary mode. So, meaning that its excitation could be either +1 or -1. Okay. So, now we can characterize this kind of a machine, okay, by an energy function. So, this is recurrent meaning that we are going to have we are going to have feedbacks, okay, feedback interconnections amongst the neurons. All right. I mean feedback connections between the neurons as also self feedbacks, okay, that is also included. Okay. But of course, I mean in the energy function that we are going to define, there the self feedback is not included. So, the energy function that we are going to define for such a kind of a network is given by E, which is equal to -half summation, this is by the definition, summation of Wkj xk xj, and we sum it up over all the j's and all the k's, but with the condition that j is not equal to k. Okay. All the j's and all the k's with j not equal to k, meaning what? That the self feedback is not considered in this case in the energy expression. So, we are not considering any wkk term or wjj term, and just simply interpret what it means. You take a neuron labeled as K, and you take another neuron labeled as J, and you have a connection from the neuron J to neuron K, and that connection is WKJ. KJ is from J to K, right? Do not make that mistake. So, it is WKJ XK XJ. So, XK and XJ are the inputs, and inputs could be either in the level of +1 or -1, okay, and there will be some WKJ, some weight will be associated, and we are summing up all these products, okay, and together that will be signifying an energy function for this entire network. All right. Now, what it means is that, I mean, in what sense is it stochastic? Okay, because we said in the beginning itself that it is a stochastic learning algorithm. So, it is stochastic in the sense that in this kind of a network, so imagine that you have got a network like this, okay, maybe some neurons, okay, which are interconnected amongst themselves. So, like this the neurons are interconnected amongst themselves, and not only that, I mean, we have drawn this picture where you can say that we can take the outputs from any of these neurons. I mean, there are how many? 3, 4, 5, 6, 7 neurons that I have drawn. So, it is a 7 neuron system, and we can pick up any neuron, okay, as output unit, or rather to say that any output pattern could be defined as a vector of all these 7 states, okay, put together. But in a general Boltzmann learning network, we could be having some neurons which do not take part in the output. So, meaning that we could be having a set of neurons which are there in the outer layer, and then some set of neurons which are there in the inner layer, which serves more like a hidden layer. Hidden layer in the sense that they do not really take part in the output, means we cannot specify, I mean, we cannot specify their states in the outputs, but we can take all these neurons, okay, for the output, right. So, basically what happens is that in that case, whenever we have got such kind of layerings that some of the neurons are available as output and some of the neurons are not available, they are hidden, in that case we just segregate the neurons into 2 categories. The ones that is available at the output, okay, let us say we mark them with a different color. So, all these neurons which I have marked with a different color, those things we are calling as the visible neurons, okay, and the ones which are there inside, okay, the ones which are not colored, okay, which are marked as black only, they are hidden neurons. Okay. So, we will be typically having visible neurons as well as hidden neurons. Okay. But what I want to discuss is that, or say for example, we may be having, in this case there is a Boltzmann network where all the neurons in the output layer, they are visible. All the neurons themselves are visible. So, there is no hidden layer in this Boltzmann network that I have drawn. Okay. Now, what the Boltzmann network is really saying is that when you have an energy like this, this energy is defined for what? This energy is defined for a particular state of the network. And what is meant by the particular state? You take a network like this, let us say, okay, and supposing you have got some particular state, say this is at +1, this is at -1, this is at -1, this is at +1, this is at +1, this is at -1, this is at +1, something like this. So, this is a state of the neuron that we can describe. Supposing we begin with this. So, +1, -1, -1, +1, +1, -1, +1, this vector, if I form it into a vector, that will define the state of this. So, for this state of the neuron, okay, we will be having some energy function, right. Now, what happens if I randomly pick up any one of these neurons? Okay. Supposing I just simply decide to pick up this particular neuron, supposing I pick up this one, and then after picking up this neuron, I change its state, I flip its state from -1, I make it to +1. Okay. Then what happens? Then we have to recompute this energy, isn't it? Because it was computed on an earlier energy, I mean based on the earlier state. Now that I decided to flip it, okay, the energy is going to change. Okay. And what happens? That there will be a total change of energy. It could increase, it could decrease, but I can pick up any one and I can make it change of the, I can cause the change of state. Now, what it means in the stochastic sense is that what is the probability, okay, that there will be a change of state for any picked up neuron k. Supposing if I pick up any neuron k, then what is the probability that its state will be flipped? Okay. That probability is stochastic in nature and it is given by this. Okay. So, probability that a neuron k flips its state from its current state xk to minus of xk, this probability is given by 1 plus exponential to the power minus delta ek by t. And what are the meanings of these terms? What is delta ek? Delta ek is nothing but the change of energy. It is the change of energy resulting from such a flip. Meaning, by applying this equation, because we decided to flip one particular xk, okay, then what is the change of energy that is there, and what is T? As usual is the pseudo temperature. Okay. So, T is the pseudo temperature which we had defined earlier when we talked about the stochastic activation units. There we came across this concept. So, what happens that depending upon these delta ek and T, okay, T will definitely signify the noise in the system, because basically the concept of the temperature comes about that with increasing temperature the network becomes more noisy, more stochastic, less deterministic, like that. Okay. So, ultimately what happens is that there will be a condition when the Boltzmann network will have a steady state. Okay. That means to say that ultimately, see, initially when you allow the network to settle, in that case all the vectors will be random. I mean there will be some random pattern that we are feeding, random weights that will be there in the system, and now it goes through such change of states, and change of states will also happen because every change of state will mean that there will be significant change in energy, significant change in delta ek will be there. As a result, there will be more probabilities of change of so as a result the change of state will happen with more frequent probabilities, but ultimately there will be a state condition when the probabilities of flips will get reduced, which means to say that the network will attain some kind of a stability. We can say that the network has attained the thermal stability. But one thing that one can tell about the Boltzmann network is that firstly that we have already classified the Boltzmann neurons into two classes. So, Boltzmann neurons we have already classified to be the visible, one that is available for the outside, and hidden. Now, one thing that we have to understand that can we change the states of all the visible neurons as per our will, or can we allow all the neurons which is available at the output layer or which is available in the visible way, can we afford to change everything? Perhaps we can, perhaps we cannot. In which case we cannot? If we happen to put some constraint on the system, because ultimately this kind of a neural network, Boltzmann network, you are going to use in some application. Now that application may put forward some constraint, okay, that these neurons, I don't want change of state to be there. Maybe that if you have 100 neurons visible, you can decide that out of that I will not be allowing change of states for these 15 neurons. These are my constraints. I am clamping it, that some of these will be permanently as +1, you can never change its state. Some of these will be permanently in -1, you can never change its state. Like that we clamp the states of those neurons. Maybe out of 100 I specify that 15 are so clamped and the remaining 85 are free. Free parameter adjustments are possible with remaining 85. And when it comes to the hidden, then there is no question of my specifying constraint, because the hidden neurons do not take part in the output, right. So the hidden neurons should always be free. So there is another classification that we are doing, that is the visible network, the visible neurons we are classifying into two groups. One is the neurons, the visible neurons which are clamped in the sense that their states are pre-decided. So this is dependent on the environment. So dependent on the environment. So depending on the environment, we are going to decide that some of the neurons will be clamped and there will be some other neurons which will be free, and hidden neurons, okay, they will be always free. Okay. Now that means to say that when we have some free neurons and some clamped neurons, okay, then how does the system learn? That is what we are going to study, right. So the learning could be defined like this, that we consider that let us say that we denote rho kj plus to be the correlation between neuron K and neuron J in the clamped condition. Any suggestion how can I mathematically define a correlation in this case? Any simple mathematical way that you can suggest? Two neurons, one is neuron K, another is neuron J. So we are going to define a correlation for that. So what is going to be a simplest form of correlation? When you are going to say that neuron K and neuron J are correlated, when their states are same, that's right. So if both of them are +1, it is correlated. If both of them are -1, then also it is correlated. But if one is +1, another is -1, it is uncorrelated. So what is the measure of correlation? You simply multiply their states, okay. So if the multiplication gives you the value of +1, then it is correlated. If the multiplication gives you -1, it is uncorrelated. So we can consider that these rho kj's also are binary quantities, +1 or -1, +1 for correlated case and -1 for uncorrelated. So we are saying that rho kj is the correlation for the neuron K and neuron J in the clamped condition, mind you, okay. And we again define another correlation parameter which we are defining as rho kj minus, okay, which is the correlation between the same neurons, okay, in the free running condition. Okay. In that case, delta wkj will be defined by, again, whatever we do for learning, this fellow is unavoidable, the learning parameter, it will be always there, okay. This eta the learning rate times rho kj plus minus rho kj minus, and again this will be defined for j not equal to k, and this is our Boltzmann learning rule. So, it is definitely a stochastic learning rule that we have decided. Okay. So, based on this factor, the WKJ, the weight adjustment will be there. Okay. But more than that, I am not discussing about the Boltzmann network at this stage, because Boltzmann network really needs some more detailed explanation, which we will see later on. All right. So, now we can afford to begin the topic that we promised for today, that is about associative memory. In fact, in the remaining time, the only thing that I can do is to give you the concepts about the associative memory. Now, just note the two words in it. I said associative and I said memory. Okay. Now, how are these two things really related? In fact, if you see the learning mechanism, okay, how do we learn? I mean, forget about artificial neural networks. Let us come to our case. Okay. How do we human beings learn? Okay. We learn a lot using association. Okay. We can always relate, I mean, based on our experience, we can relate that this is something that I had seen there. Okay. Supposing in front of me I have got students from IIT, okay, who are attending this course. Okay. Now, there are a large number of students. I may not be able to recollect the names of every students. Okay. There are 80 or 70, 80 students in this group. So, then what happens, that supposing I see one of the persons in the market. Okay. Now, what I am going to do? I am certainly not going to recall the name of that person, because I mean, I may not be knowing the name. I mean, unless he is a very familiar person, I mean, a student whom I have observed for I mean 1 year or 2 years, or he or she attended my earlier course. So, I may be able to recollect the name immediately, but then what I am going to do is that I will think that yes, it is a very familiar face, and where have I seen this person? Okay. So, then I recollect that yes, I have seen him in the class. He is the person who is attending the neural network course. Okay. So, there is a kind of an association that I am making, that okay, for the neural network course I have got an association that okay, whenever that face is presented to me as a pattern. So, what is that face? That face acts as an input pattern to me, and then I put him into the category that okay, I have seen him in the neural network class. Okay. So, there is a kind of pattern association that we are doing. So, it is actually whenever we are associating anything, we are recalling from our memory, and then only we are associating. Okay. Now, what is the concept of a traditional memory? Because memory all of us understand, because nowadays I mean everybody is using computers, okay, and we know that computer has got large amount of memory. Okay, we have got memory in the form of RAM, we have got secondary memory in the form of hard disks and whatnot. So, then what is the difference between this memory and that memory? Now, there we feed the address of the memory. There every memory, the memories are actually arranged in continuous locations, and every memory location will be having some address. So, I will be giving the address of that memory, and then I will be retrieving the data corresponding to that address, okay, and I will use that. Okay, that is what we are doing for all our computational purpose. Now, here what I am doing is that I am not feeding the address. I do not really know that, I mean, if my brain has got a large amount of storage space, I am not really remembering, or it is not possible for me to specify that where in the memory, which address location in my memory did I store this person's face. It is not possible for me to know. I see the face, that face acts as a pattern, that face acts as a stimulant, and based on that stimulant I go over to the memory and then get it. So here it is something like the retrieval that I am doing from the memory is based on content. The pattern is a content. I am accessing that and then I am able to retrieve the data out of that. Okay. So really speaking, we are feeding the content and then we are getting the response from that memory. Okay, that yes, this content I have seen him in neural network course. This content, okay, I have seen him in the department office. This is the pattern content. Okay, I have, I mean, he is a shopkeeper somewhere. Okay, I have seen him. So this is the kind of an association that we are making. So it is a memory that involves very much the association, and I think from all this discussion you can very easily understand that it is in fact, I mean, the process of association and the process of memorizing, they are very much interrelated to each other. The process of learning and the process of memorizing, they are very much interlinked to each other. Now let us see that what kind of memories do we have, especially the memory of our brain. Okay. Now it is seen that the memory that we use, okay, can be divided into two broad classes. One is a short term memory, okay, and the other is the long term memory. Okay. Now if I ask anybody in the class over here that what was the menu for today's lunch, okay, you are definitely going to tell me, isn't it, that okay, the menu was this, that we had rice, we had dal, we had chapati, we had some sabji curry, something. Okay. So you will be able to tell me from your short term memory. Now if I ask you the question that what was the menu for you on Monday, will you be able to give me the answer? You will simply say that no, we don't remember what was the menu for Monday lunch or what was the menu for Tuesday lunch. I mean 3-4 days back, whatever menu was there, even yesterday's menu we will not be able to tell. Okay. So why can't we tell? Because it is in the short term memory. But if I ask you that in which year did you appear for your high school leaving examination, are you going to make a mistake on that? Never. Okay. If you have passed out your schooling in the year 2000, you are going to say that yes, it is year 2000. Even if I ask you 15 years from now that in which year did you have your school leaving examination, you are going to say that it was in the year 2000. Okay. You are never going to forget that. In which year you got into IIT, you are never going to forget that. That means to say that this is something that goes into your long term memory. So we have got these two categories, the short term and the long term. Okay. Now one thing, that why is the short term really a short term? Okay, let us also try to understand that, because the short term memory is all the time indicating some current information, the very latest and current information, okay, which is going to be updated and corrected all the time. Now why can't you remember the menu, okay, of your lunch? Okay, I mean you can remember only the menu of today, I mean which you have taken just a few hours back, you took your lunch, so you can remember the menu. But why can't you remember for 1 or 2 days back? Because it is getting updated all the time with the current information. So it is not possible for you to, I mean, retain all these things into your long term memory, and there is no point. In fact, I mean there is a kind of intention also that goes on. I mean, I don't think that anybody will deliberately try to remember the lunch menu, and that too when it is hostel lunch. Okay. Anyway, so let us see the aspects of associative memory. So all that we can cover at this stage is some characteristics of the associative memory. Okay. So we list out some characteristics. The first characteristic is that the memory is distributed. Okay. And what is meant by distributed? Very simply, that it does not lie in one particular location, means all the memory locations, okay, are not lying in one particular place. They are distributed. Even in our brain, okay, the neurons are distributed all over the brain, okay, and this is highly distributed in nature. In fact, what happens is that together we are feeding some input activity pattern. So there is some input activity pattern that we are feeding as a stimulus to the system, okay, and then the system or our brain or whatever you say, or artificial neural pattern, whatever you think of. So it gives some output activity pattern. So there is a mapping that takes place from the input activity pattern to the output activity pattern, okay, and this happens in a distributed memory environment. Okay. We will come to that, I mean we will come to the details of that soon. Okay. And then the second characteristic that we can say is that the stimulus pattern. What is meant by stimulus pattern? The input, okay, like little while back the example that I was giving you, the stimulus pattern is the face of the person whom I am seeing right now and I am trying to associate. So stimulus pattern, that is one pattern, and then we are also going to have a response pattern. Okay. Now what is the response pattern? Again, it is not only that I know that I have seen this person in neural network class, but also more or less I will be able to predict some more things. Okay. Maybe that normally this particular person sits on the left hand side of the class, okay, or normally this is the person who sits on the front bench, normally this is the person who will sit somewhere in the middle row, okay. Normally he prefers to sit on the extreme right hand corner of the class, like that. So there is a response pattern that also we get, that once a stimulus is presented, okay, we are also going to get a response pattern. Okay. Then the information contained in the pattern, so stimulus pattern and response pattern, they are in the form of data vectors. Now this is quite obvious. Why is the stimulus pattern a vector? Because stimulus pattern is, in this example, for a I mean let us take that example, the face image, okay, it is a stimulus. So what is that? It contains a data, I mean it contains a pixel data, okay, that every, I mean at every picture element we are having some intensity, some color and all that, okay. So that is a data vector at the input, and response vector, again that is also a data, it is giving that in which particular location this person sits and all that, okay. Then the information not only contains the storage location, but also its address for retrieval. So information contained in the stimulus okay, also determines its address for retrieval, and then another very important aspect is that it has got high degree of resistance to noise. What does it mean? This means to say that I mean, although the neurons are doing the ultimate processing, isn't it? The neurons could be operating under noisy conditions. I mean, we could be operating the neurons in a stochastic way, but even then, okay, our associative memory works in a mode that it has got very high degree of resistance to noise. So, although the neurons themselves will be noisy, but still the classification that we are making, the association that we are making, is highly resistant to noise. Okay. And then the last point that we would like to mention about the characteristic is that there is a high degree of interactions between the patterns. Okay, high degree of interactions. Okay, and that often leads to errors during recall process. Now, I give a simple example to that. Okay, I think it happens I mean many times in our real life. Okay. Now, I mean somebody had once asked me that, hey, I think you are working in Syndicate Bank Bombay branch, isn't it? I have seen you over there. Now, I am surprised that no, I am certainly not an officer or employee in Syndicate Bank, and that too posted in Bombay. Okay, I am a simple person living in IIT Kharagpur. Okay, I am just teaching over there. I am not a bank officer. They said, no, I think I have seen you. So what happens is that maybe that my face, okay, looks very similar to somebody who is working in Syndicate Bank Bombay branch. Okay. So they say that, I mean, somebody recollects wrongly. So what happens is that there is a very similarity in the pattern. Maybe that, I mean, because my face resembles another person, okay, people make a wrong conclusion. It's quite possible. So there are interactions between the patterns, okay, and also another thing which is going to happen, that there is a definite learning capacity up to which we can learn, and if we try to go beyond that, okay, there could be errors in the recall process. In fact, we are going to see all these things in terms of artificial neural network behaviors, okay, in the next class. So this is just only an introduction to the associative memory. Thank you.